All right, so today is Wednesday, April 29th. We're going to be working on sample proportions. And basically, the one thing I would say about this is you can bet that there's going to be a lot of them on here, or excuse me, you're going to bet that I'm going to be covering a lot of them. And I think there's a fairly high probability that this will show up on the test. Do I know that? No, I don't. We're going to cover 4 problems today. They're fairly lengthy. And then on Friday, we'll cover the remaining 4. Please remember there will be a Stat Saturday this Saturday, and it'd be very, very beneficial if you actually had completed Stats Medic Unit 6 and 7. Not required, but it would be to your benefit to have done that. Okay, so we did problems 1 through 4 in our last meeting on Monday, and those are posted online. Today we're going to start with question 5, and we should get through 5 through 8. So a large university provides housing for 10% of its graduate students to live on campus. The university's office thinks that the percentage of graduate students looking for housing campus housing may be more than 10%. So we're going, okay, it's more than 10%, or we think it might be. So the housing office decides to survey a random sample, thank you, of graduate students, and 62 of the 481 students say they are looking for housing on campus. So, on the basis of the survey, would you recommend that the housing office consider increasing the amount of housing on campus available to graduate students? Give appropriate evidence to support your recommendation. All right? So, first off, a lot of times people have trouble determining whether or not this is going to be a test for means or a test for proportions. So I kind of like to talk about that real quickly. They gave me 2 values, which is great, 62 out of 481. Neither one of those is a mean, and neither one of those is a standard deviation. If you're only going to give me 2 values, one has to be a mean and one has to be a standard deviation. And really, I'm also going to need a 3rd value, is the sample size. So because I don't have mean and standard deviation, can't be a test of means. So I'm kind of stuck with the test of proportions. So on the basis of the survey, they say they believe it's been 10%, and now they think it's greater. So that's going to be my null and alternative hypothesis. So my null is it's 10%. My alternative is greater than 10%. PO is the true population proportion of graduate students looking for campus housing. Awesome. Then I need to know through my conditions. First conditions, random sample. And they told me it's a random sample of 481 students. It's given in the problem. If I just said random sample and given in the problem, that's great. Then I need to check that it's less than 10% of the population. So N is less than 10% of the population. To check that, I take the sample size of 481, and I either multiply it by 10 or divide it by 0.1. And I get 4,810. And then I make a comment. It's reasonable to assume that there are at least 4,810 graduate students. Obviously, this is a fairly large university. Then I need to talk about NP and NQ, which is basically, is my sample large enough in order to use the normal approximation? Now, I want to back up a little bit on this, and NP should look familiar to you. And here's why. Because when we talk about the binomial, the expected value is NP. So this is essentially how many people out of 481 would we expect? But we don't have to expect, in this case, because they didn't give me a percentage, they told me how many people. So I know that we expect 62 because that's what we got. So that's NP. Make sure if you use Q, you can always use 1 minus P, but if you use Q, make sure you say what it is. So NQ is 481 minus 62, or 419. That's greater than 10. So both parts are satisfied. So the sample is large enough to use the normal approximation. I need to come up with a p-hat because p-hat's utilized in my formula. Well, p-hat is just the number of successes divided by the sample size. So 62 divided by 481 gives me 0.1289, or about 13%. So there's my formula, and that'll be, you'll have access to that somewhere or the other if you haven't memorized it. So 0.1289 minus a 10%. Now this is where we have to be careful. Please notice I used 10% there. It's P naught in this formula. And it's why? It's because our null hypothesis said, hey, this is what we initially believe, so we go with what we believe until we prove otherwise. So then I go about running my test, which is going to be just a stat test, one proportion z test, and we have 0.1 is the p-value, that's the claim. My x value was 62, and my sample size was 481. And we are looking to see if it's greater than, I'm going to change that color back, I like blue. There we go. And I'm going to go ahead and calculate this thing. And I end up getting 2.11 for my z-score. And I ended up getting a probability of 0.0173. So p-value 0.0173 is less than alpha, we reject a null. Then we make our conclusion. Our p-value is 0.0173, we reject a null. There's sufficient evidence at alpha equal 0.05 to suggest that the true population proportion of graduate students who would like on-campus housing is greater than 10%. That's great. Unfortunately, there's something I left off here, and I did it intentionally. The question was, would you recommend considering increasing the amount of housing for graduate students? Give appropriate evidence. I gave the evidence, but I didn't answer the question. So make sure you always answer the question. Those are easy points to lose. So in this case, we rejected the null of 10%, so I should sit there and come back and add, we would recommend adding more housing. All right, make sure you always answer the question. Sometimes we get so caught up in the stats part, we miss the easy part. Don't do that. In addition to the 481 students who responded to the survey, there were 19 who did not respond. If these 19 had responded, is it possible that your recommendation would have changed? Okay, so in my case, I use an alpha of 0.05, so I rejected. All right, so I need to sit there and see, well, what is there a chance that I would fail to reject? Well, if I fail to reject, that means I want there to be a smaller percentage. So to do that, I'm not going to add to the 62. I'm just going to add the 19 to the 500. All right. When I add the 19 to the 19 to the 481, I get 500, and I now get 0.124. I run the same value, I run the same test, and I'm going to go ahead and run that real quickly. Stats test, one proportion, z test. We're still working at 0.1. We still have 62 who won it, but we added the 19 to the 500. All right. And we calculate it, and we end up getting 0.037, which is still less than 5%. So in this case, the decision would not have changed. Remember, don't just show your work. You have to show your work, but you also need to address the decision. All right. So that will take care of problem number 5. Now, one thing to talk about, I guess I should talk about, is what would I have done if I'd used an alpha of 0.01? In this case, we would have failed to reject. If I'd used 0.01, we would have failed to reject, and so then we would not have recommended adding more housing. But where it gets a little tricky is when I come back here. All right, so in addition to the 481 students, there were 19 who did not respond. Well, now I'm still going to add the 19 to the 500, but I'm going to say they all wanted it, in which case I'd have to add the 62 plus 19 and then run it. But that's if I'd use an alpha 0.01. So make sure you're always checking that. I doubt that they give you one that tricky on part B. Part A, I think, is a very, very fair question, and probably actually a little easier than I would expect. All right, question number 6. Actually, you know what? I should back up. On question 5, do y'all have questions on that y'all would like to ask at this time? And yeah, you are on record. I can go ahead and knock that record off just a second. Just a second. Let me stop the recording or pause. Okay. A random sample of 415 potential voters was interviewed 3 weeks before the start of a statewide campaign for governor. 223 of the 415 said they favored the new candidate over the incumbent. Great. All right. However, the new candidate made several unfortunate remarks 1 week before the election. Subsequently, a new random sample of 630 showed that 317 favored the new candidate. By the way, they told us these were random samples, which was nice of them. Do the data support the conclusion that there was a decrease in voter support for the new candidate? Give appropriate statistical evidence. So here's the situation. We have 2 surveys. All right, the question is, are they proportions or are they means? Well, first off, they'd never mentioned the standard deviation. They never mentioned the mean. So consequently, since I only have 2 values for each one, it must be proportion. So that's a proportion. That can be done as a proportion. So I can compare 2 proportions. In order to be 2 means, a test of means or a t-test, one of these would have to be a mean and one of these would have to be a standard deviation, but that's not what they gave us. So that lets me know I'm working with 2 proportions. All right, or that's one of the easier ways on this one. So define the proportion. P1 is the true population proportion of voters supporting a candidate early in the campaign, and P2 is supporting later. Now, you can use letters here and probably should. Early and let E for early, L for late, or something like that. For ease of typing, I just use P1 and P2, but that was mainly for my convenience. Use what makes sense for you. So conditions. Random samples are given. And I probably should have put 2, but 2 random samples are given. First random sample of 415, and second random sample of 630. You only needed to say 2 random samples were given. All right? Reasonable assume that the polls are independent. And matter of fact, it's really important to talk about the independence, but you can actually, they're actually pretty good about letting you say 2 independent random samples. And you don't even necessarily have to directly address the independence issue if you do that. And the thought is this: if the polls are independent, if the polls are random, then one poll should not impact the other poll. That's the thought, okay? But you need to make sure you do address it independence. Whether you address it as the second one or combine the 2 together will be fine. Then, because we're working with proportions, we need to make sure that our sample is large enough to use the binomial. Well, first off, we need to exceed, First, we need to make sure we don't exceed sample size. So 415 divided by 0.1 is 4,150. And it's reasonable to assume that it's for a governor's race, there's probably more than 4,150 voters. Now, the reason we do this, the N is less than 10%, is because we're sampling without replacement. And consequently, when you sample without replacement, it's that giant pile of M&Ms. I take an M&M away, technically the percentage changes, but does it change by too much? This this indicates that it doesn't change by too much because it's less than 10%. As long as it's less than 10%, we say it doesn't change by too much. And when the second poll was a little bit larger at 630, but once again, we'd expect it to be at least 6,300 voters. Now we need to talk about normality. And this is whether or not our sample is big enough. And so this is when we're going to go the expected value in P. And they told us that we had 223 that were in favor in the first poll. So 415 minus 223 is 192. Both of those are greater than 10. This side complies with what's necessary. Here we have 317. That's also greater than 10. 630 minus 317 is 303, which is greater than 10. So basically, both samples are large enough to use the normal approximation. And once again, on the previous problem, I alluded to that the expected value is in P. And that is basically the formula for a binomial, which when you're working with proportions, this is technically a binomial, but we're using the normal approximation for the binomial because our sample size is large enough. All right, so I need to come up with P1 and P2. P1 is 223 divided by 415, or 0.5373. P2 is 317, 630. So we see that we went from 530 or 0.53 to 0.50. So right now we look at it and go, you know what? It does look like his poll numbers have decreased, but is it statistically significant? All right. Well, when we're doing with two proportions, we actually have to pool or combine proportions. All right. So the number of people that supported him, or the number of people in sample 1 is 415. The number in sample 2 was 630. Those that supported in poll 1 is 223. Those that supported in the second poll is 317. So that ends up giving us a probability of 0.5167. So our combined probability is that. And then we get to our ugly formula. And once again, this will be on a recipe card and on the formula sheets. So here you go. There's our formula. P combined, 1 minus P combined. P combined, 1 minus P combined. Or you could just define Q combined up here if you wanted to. So I plugged in my values, 0.5373 minus 0.5032. Combined, 1 minus that. Combined, 1 minus that. Sample size is the first sample, sample size is the second. And so then I need to go about solving that problem. So stats test two proportion z-test. And my sample for the first one, we had 223 out of 415. And for the second one, we had, where was my value? 317 out of 630. And they want to see if it decreased, so make sure that you're always using the inequality in your alternative statement, which I have. And I end up getting a z-score of 1.081 and an associated probability of 0.1396. So about 13–14%. Well, that p-value of 14% is greater than our alpha of 0.05, so we failed to reject. We write our conclusion. Our p-value is 0.01397. We failed to reject a null. There is not sufficient evidence that alpha equal 0.05 to suggest that the true population proportion of voters in favor of the candidate was greater earlier in the campaign than it was at the end of the campaign. But what was their question? I need to make sure I answer their question. Do the data support the conclusion that there was a decrease? So my answer to that is we cannot claim the candidate is losing support. All right? We cannot make that claim. Now, it is possible that if you had swapped the order of these, you could have done it as a less than. I did it as a greater than. It depends on how you want to do the test. It depends on how you set it up and how you define your variables. All right? because basically we're saying early in the campaign he's more popular than later, but if you set it up, later is less popular than early. You can do that, okay? So with that said, that's one thing that I'm not used to is the Zoom thing always slides off. So I'm gonna, okay, problem number 7. It's a question 6, which means this is a long problem, and this is a very long problem. So a survey given to a random sample of students at a university included a question about which of 2 well-known comedy shows S or F students preferred. So when I say S or F, I immediately think of Seinfeld or Friends, but someone suggested to me it could have been The Simpsons or Family Guy. So I guess that's also a possibility. But I'm going to go with the Seinfeld or Friends. But the students were asked the question, do you prefer S or F? The responses are shown below. So 185 preferred S, and 139 preferred F. So just based on that evidence, just looking at that, I'd go, well, more people prefer Seinfeld or S or Simpsons, whatever the case is. All right? So based on the results of the survey, construct and interpret a 95% confidence interval for the proportion of students in the population who would respond S to the question, do you prefer S or F? So the very first thing I do is I start off, let P equals the true population proportion of students who prefer S. My formula is as follows. Please notice that here I'm using P hats. And the reason I'm using P hats and not P naught is because it's a confidence interval and I don't know what the proportion is. I'm using my sample to estimate the population. So consequently, I have to use P hat and there is no claim. And when we do a hypothesis test, there is a claim. So we use the claim until we prove it false. Here, there is no claim. They just want to guess, and they're going to use our sample as their best estimate. Please make sure if you use Q that you define it. Condition, random sample of 324 students is given in the problem. We need to make sure our sample is not too big, that we maintain independence. So N is less than 10% of the population, so 324 divided by 0.1, or 324 times 10, doesn't matter. A reasonable assume that there are at least 3,240 students at the university. Then we need to check to make sure that we're large enough to use the normal approximation. Well, we know that 185 said yes, that they prefer S, and 139 said that they prefer F. So basically, both are greater than 10, we're good enough. All right, we're large enough to use the normal approximation. Once again, they did not give me P hat. And you know what, I'm gonna restate something real quickly, just because I haven't said it today. Make sure X and N are always whole numbers. If they're not, round them. Which, how do you round them? I tend to round them to the way that I was taught in elementary school, but as long as you round them and make them whole numbers, you're gonna be good enough. So if you round it down when you should have rounded up, you're gonna be okay. But please do round, all right? The X and N, your calculator will not work properly if they're not whole numbers. It will sit there and go, error, and you're gonna be all frozen up and it's gonna scare you, and I don't want that to happen. So in this case, 185 out of 324, so we ended up with a 0.571. All right. And obviously I have a typo somewhere. This should be a 0.571. So P hat is 0.571. We needed a 95% interval because that's what they asked for. Please remember we're working with a Z because every time you work with proportions it's a Z. The second vars, inverse norm, parenthesis 1 minus 0.95 divided by 2. So this gives me a Z star of 1.96. And this should be 0.5171 times Q, or 1 minus that, over 324. And if we go ahead and run this test, stats test, one proportion Z interval, X is 185, N is 324. Oops, pushed it too many times. Got all excited. Getting to do stats early in the morning. What could be better? Please don't answer that. All right. So I end up with the interval 0.5171 to 0.6249. And that just came straight off the calculator. All right. So we are 95% confident that the true population proportion of students who prefer S lies within the interval. And we just stated it. We're good to go. Then it says, what is the meaning of 95% confidence in part A? In repeated sampling, we would expect that our method would capture the true population proportion of students who prefer S about 95% of the time. All right. Again, these are easy. That's an easy sentence and gets you full credit every time. One thing they didn't ask on part A, which I'm going to mention now, is there sufficient evidence to say that people prefer Seinfeld over Friends? And I'm going to sit there and go, well, 50% is not contained in the interval. Because 50% is not contained, there is evidence that they prefer Seinfeld. And you go, well, why did you choose 50%? I chose 50% because we have two different choices, A or B, and if it was equal, both would have 50%. So if you had two candidates running and they tied, each one would have exactly 50%. Here we have essentially two candidates or two shows, and if they were equal in popularity, both would have exactly 50%. So 50% would need to be in its interval. Since the interval is above it, I'm going to say Seinfeld was more popular based on this sample. But we have another part to the problem. In part C, the follow-up survey, a separate group of randomly selected students was asked, do you prefer F or S? Whoa, wait a second. What's the difference? The difference is, previous one, they said they preferred S or F. Now they just asked the same question, but they swapped the order. And look what happened. Friends was preferred more than Seinfeld. Wow, that's interesting. So one said the first had more people in favor of Seinfeld. The second, when you swap the order, had more people in favor of Friends. So based on these two surveys, part A and part C, is there evidence that the stated preference depends on the order in which the comedy shows were listed? So I'm going to sit there and go, gosh, I don't know really what to do, but I know I have two proportions. If the proportions are the same, then there's no difference. If the proportions are different, then something changed, and the only thing that changed or appears to change is the order. All right, so P1, the true population proportion of students who prefer S when it is the first choice. And P2 is the true population proportion of students who prefer S when it's the second choice. Technically, you could have run it using F as opposed to S, but since problem A asked about S, I thought I'd be consistent and use S again, all right? Besides S for Spencer, so I have to do that too. I know, stupid and corny, but I'm trying. So random samples given, first random sample of 324 and second random sample of 156. I could have said two independent random samples, but I address independence here. Reasonable to assume that the samples are independent, as one sample result should not impact the other. And that's probably a true statement. But I could have just said two independent random samples, and that would have taken care of that. So I need to check, make sure my sample isn't too big so that independence between sampling is taken care of. We already answered it for part A, so I'm not going to talk about that one because we did that on part A. But here we're going to address it here. And we have 156 divided by 0.1 is 1,560. Reasonable to assume that there are more than 1,560 students. All right. Moving along. We've already addressed whether part A was big enough, or whether the first one was big enough to use a normal approximation. But now we need to look at the second. Well, we have 68 in favor of Seinfeld here, and 88 who were in favor of Friends. Both of those are greater than 10, so they're both samples are large enough. So we can look at this and go, yay, we're big enough to use the normal approximation. Like, once again, I need to set up my how many people are in favor of each. And so we have 185 out of 324. And then we have 68 over 156. All right? And so the first proportion was 0.571, which is what we had in part A. The second one from the second survey is 0.4359. We notice a big drop from 57% to little 43.5%. That's a pretty big drop. Once again, since we're working with two proportions, we have to pool or combine them. And I end up plugging in, there's my sample sizes. Those are the people who preferred S, first sample, second sample. And we say, all right, we still have a preference for S, and it's at 0.5271. So plugging into my formula, I have my first proportion here and my second proportion there. And then my combined, 1 minus combined, combined, 1 minus combined, first sample size, second sample size. Please notice I put a 2 times, and there's a reason why I did that. The reason why I did this is because this was a not equal. If it had been a greater than or less than, I wouldn't need the 2 times. Please don't forget the 2 times when you're working with a not equal. So let's go ahead and run this test. So stats test, 2 proportion Z interval. This always makes me nervous because it's a long scroll to get there. And we had 185 out of 324 for the first sample. And for the second sample, we had 68 out of 156. Oh, I'm sorry, it's supposed to be a Z test, not an interval. Stat test, 2 proportion Z test. 68 out of 156. We're looking for a not equal. And I ended up getting the Z-score of 2.777 and a p-value of 0.005. That's a pretty small p-value in that it's less than 1%. All right? So with a p-value that small, we're going to reject the null. So our p-value is 0.0055. We reject the null. There is sufficient evidence to suggest at alpha equal 0.05 that the true population proportion of students who prefer S differs depending on whether it is the first or second choice. So, does it make a difference? Yeah, we believe that the order of the choices affects the responses. And that was the question that they really asked us. This would probably take care of us. This definitely takes care of us. All this other work is justification. However, because I said who prefer program S differs depending on whether it's the first or second choice, probably sufficient in this case, but always good to have a single summary sentence that makes it very easy to understand. All right, so we're moving on to part D. Part D, and I just told the people that are in my Zoom meeting, is a challenging question. And honestly, I don't expect anything like this to show up on the AP exam. So I expect that they're going to ask me a lot of questions off camera or after the recording's over. If you don't understand part D, don't stress it. That's all I'm going to say about that. So suppose the test in part C indicates that order in which the shows were listed does make a difference. And in fact, that's what we showed. Is the pool value or the combined value a reasonable estimate for the proportion of students at the university who would respond S? or Seinfeld? If so, justify your answer. If not, what would be a more reasonable estimate? Well, this is what we used. That is absolutely what we used in part C. Now the question is, under what conditions do we use that? Well, one, we have to have two proportions. And the reason we use this is because this is the claim of the null hypothesis. There is a claim of them being equal. And if they are equal, this is appropriate. But we ran the test and showed that they were not equal. And they said right here that it does make a difference. So because it does make a difference, this is no longer a good estimate. As long as we believed this, it was a good estimate. So we ran the test correctly. We did everything right in part C. But now that we know that there is a difference, that order does matter, this is no longer a good estimate. So they ask us to justify that answer. So if I'm going to do that part, and then in the next part it says, if not, what would be a more reasonable estimate? Pooling is based on the assumption that the population proportions are equal. In part C, we determined that the proportions were not equal. Thus, we should not use the pooled result as our best estimate of the proportion. Great. We said they weren't equal in part C, therefore we shouldn't use this. We only use this if that's the case, if they're equal. So how would I do this? This is where it gets really difficult to understand. A better estimate would be to equalize the sample size. Well, what do you mean by that? Well, I had two sample sizes. I had a sample of 324 and a sample of 156. So I sit there and go, hey, you know what? Sample one was about just a little over twice as large. So I need to multiply, I need to equalize the samples. So I can either divide the first sample by 2 or multiply the second sample by 2. I mean, either I can divide the first sample by 2 or multiply the second sample by 2. I can choose either one. I choose to multiply. So this was my first sample. But my second sample, I multiplied by this ratio and multiply numerator and denominator, and then combine. When I do that, I get these values, and what I find would be my best estimate based on the two surveys is 0.5034. And the reason I needed to change was because we know, or they told us, that P1 did not equal P2, and that order mattered. All right, again, I'm sure I'm going to have a lot of questions offline on this, and if you don't understand that one at home, don't worry about it. You can go ahead and skip that. Don't stress that part.